This thing here is called a Sierpinski triangle, one of the most famous and simple fractals out there. And just looking at it, it's of course a two-dimensional object. Unfortunately, proof by looking isn't a widely accepted form of proof, so we need some more rigorous evidence that this shape is 2D. Okay, I mean if you want to specify a certain point on this triangle, you'd need to give me two numbers, an x-coordinate and a y-coordinate, so it has to be 2D. But the pedantic among you might argue that this line here, as seen in the Cartesian plane, requires an x and a y coordinate for its points as well, and that's very clearly only 1D. They might argue that a shape is only 2D if it has an area. So, just to double check, we can calculate the area of our Sierpinski triangle and verify that it's finite and non-zero. In its current form, that's basically impossible to do, so let's consider how to form this triangle. One way would be to start with an equilateral triangle, split it into 4, and then remove the middle triangle. Then you would do the exact same thing with your 3 smaller triangles, and so on and so forth ad infinitum, each time reducing your area by 25%. After n iterations of this process, the area will be given by this formula here. And so the total area of the Sierpinski triangle, which is what you get after infinitely many iterations, will be 0. Okay, so maybe we were wrong, maybe it's just 1D. I mean, after all, once you cut out all these triangles, you're sort of just left with some lines, no? In fact, this is another way to think about the construction of the triangle. You start with a normal equilateral triangle, draw another one inside of it, increasing the total length of the shape by 50%, and so on and so forth. And great. Now we've got an infinite length. Well, desperate times call for desperate measures. Why don't we plot this on a graph? It's a weird graph, it's discontinuous, it's got infinity and 0 as the only y values, but it tells the tale of our triangle pretty accurately. Now let's draw up the same graph for a square. We know that a square has no volume, and if you try and cover it up with loads and loads of lines, you'll find that it has an infinite length. But when the dimension is 2, it has a finite non-zero area. And looking at this now, you might be tempted to draw a line through these points. Maybe you're imagining something a little bit like this. Now I'll tell you that that's not how this graph looks. Instead, it looks like this, with the discontinuity right here at 2. So if this is what it's like for a square, the question is it the same for the Sierpinski triangle? We're going to start with the easiest way to calculate dimension. You take your shape, double its side length, and count how many copies of your original shape are in your new shape. Let's call this number n. Then you use the handy formula 2 to the d equals n. So with a line to double its length, we need 2 lines, so d, the dimension, is 1. For a square to double its side length, we need 4 squares, so the dimension will be 2. And for the Sierpinski triangle to double its length, we need 3 triangles, so the dimension is going to be log base 2 of 3, which turns out to be around 1.585. So there's your answer. It is the same for the Sierpinski triangle, and its graph looks like this. Okay, enough of the easy stuff that everyone else has done. Time for some needlessly complicated, real maths. This number here, this 1.585 we've come up with, is known as the Hausdorff dimension, named after Felix Hausdorff, who real ones will remember from my video on Jordan curves. To understand this dimension, we need to take a few steps back and start with something called the Hausdorff measure. The Hausdorff measure is quite closely linked to both measure theory and topology, but for our purposes you don't need to know about either of them. And actually, I lied, we need to take a few more steps back to something called the Hausdorff outer measure of dimension d bounded by delta. And this long-winded thing is kind of like a function, except instead of taking in a number or whatever, it takes in a set whose size you're trying to measure. So for example, let's say that our set is going to be this 2D region right here. Then what we do is we create these things called open covers. They're sets with a diameter less than delta, which is to say that the furthest distance between any 2 points in them is less than delta. So you take your open covers, and you use them to cover the entirety of your original set. They might overlap, that's okay, but you need to have the entirety of the set covered by at least one of your open covers. Then you take each open cover, raise its diameter to the power d, which in this case would be 2 because we're in 2 dimensions, and add up all of these values. At this point you've got a number, but this still isn't the output of our measuring function. The output is the lowest possible value you can get from this process, i.e. the most efficient possible covering of your original set. So whilst that long, convoluted method sinks in, here is the proper mathematical definition of the formula, which encodes everything I just described. This bit here means infimum, which for our intents and purposes just means minimum. This bit here ensures that the covers are sufficiently small. This here is the one telling us that our open covers have to cover the original set. And this bit here is the summation of all the diameters to the power of dimension d. Now, one weird thing you might have noticed is that this is an infinite sum, even though we very much do not require infinitely many covers to cover all of S. But the reason this is written like this is because of what we're going to do next. We define the Hausdorff measure of S with dimension d as the limit of the Hausdorff outer measure as delta approaches 0, so as the maximum size of our open covers shrinks right down to 0. And then we can, at last, properly define the Hausdorff dimension of S as the unique value for which the Hausdorff measure is finite and non-zero. But how do we know that there's only one value for which this occurs? Why couldn't the dimensional graph look something like this instead? It's proof time. Let's assume that the Hausdorff measure has a finite non-zero value for some positive real number b, and let a be less than b be less than c. Wow, I should pick some other letters. But if we just focus on c and b for now, and we take a single one of our open covers, ui, we can say that the diameter of ui to the c equals the diameter of ui to the c minus b times the diameter of ui to the b. That's just your basic exponential rules. Considering the condition of the Hausdorff outer measure, we know that the diameter of ui is less than delta, so the diameter of ui to the c minus b must be less than or equal to delta. Then we can sum over all our possible covers, which we can do because we're just adding up positive numbers. In fact, we can do this over infinitely many covers to get this inequality here in terms of the Hausdorff outer measures. And we can do the exact same process with a and b to get this similar inequality in terms of a and b. Alright, so we're going to take that first inequality of ours and apply the restriction that the Hausdorff measure in dimension b of S is less than infinity. So this term right here is less than infinity. Then as delta approaches 0, this term is also going to approach 0, and by the inequality we get that the Hausdorff measure in dimension c is going to have to be 0. So for any number greater than b, the Hausdorff measure is 0, so we've got this side of the graph all proven. Now we look at the second inequality and apply the restriction that the Hausdorff measure in dimension b is greater than 0. So this side here can't be equal to 0. But since this term here still approaches 0 as delta approaches 0, what that means is that the Hausdorff measure in dimension a has to be infinity. Now this mathematical line of reasoning might look really dodgy, but I promise it works because we're just considering a limit as delta approaches 0 and not actually evaluating it when delta is 0. And it's not a strict inequality and blah 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 blah. Please trust me, I don't really know how to prove it properly, who knows. So that more or less ad hoc kind of sorts out the left side of the graph, proves our uniqueness, and now you know how to properly define the dimension of an object. Finally, it turns out that the Hausdorff measure is essential to understanding fractals, because the technical definition of one is a shape whose Hausdorff dimension is greater than its topological dimension. I can't be bothered to define topological dimension, but it's basically the dimension the shape seems to have once you zoom in far enough. So for example, if you zoom in really far into a Sierpinski triangle, it just looks like a line. So the Sierpinski triangle has a topological dimension of 1, and since 1.585 is greater than 1, that means it counts as a fractal. But what's also cool is that this can be used to categorize fractals even when they aren't self-similar. And probably one of the more famous examples of this would be the coastline of Britain, which I'm not going to draw out because I have not got the time for that. But anyway, that's all for today. Thanks for watching.